Draw the shear and moment diagrams for each member of the frame. Assume A is fixed. The joint at B is a pin and support at C is a roller. To do this problem, we're going to solve for each part separately. Alright, so let's begin with section BC. We're going to draw its free body diagram. So C is a roller, and then B is a pin connection. And we have a concentrated load, 12 kilonewton, halfway through. If we take moment above, if we take vertical equilibrium equation, we'll have to sum the forces in y direction, pretty much. And we're going to have our By as equals to 0. And then to solve for Bx, we're going to take moment above the point C. So we're going to have 12 kilonewton counterclockwise, 1.5 meters away. And then we have clockwise Bx, 3 meters away, all equals to 0. Solving for Bx, we're going to have our solution as 6 kilonewton. And now if we sum the forces in y direction, x direction, we're going to have our solution for Cyx. We're going to have 6 kilonewton, negative 12 kilonewton, and positive Cx equals to 0. Solving for Cx, we have our solution as 6 kilonewton. Now we can proceed to the next section, AB. For AB, A is a fixed connection, so we're going to have both horizontal and vertical directions, plus we can have moment. And then we have a distributed along the beam, which is going to be 6 times 4, which is 24 kilonewton. And then B is going to be 6 kilonewton in the x direction and 0 in the y direction. Now to solve for the x direction, we simply have to sum the forces in the y direction. And in doing so, we can have our solution as 6 kilonewton for x. And then to find a solution for y, same thing, we're going to sum the forces in y direction. We're going to have AY as 24 kilonewton. And then finally the moment A, we're going to take moment above the point A, solve for moment A. So we're going to have negative moment A, negative 24 kilonewton times the 2 meters equals to 0. Solving for moment A, we're going to have our solution as negative 48 kilonewton meter. Now we have all the required forces we needed for this problem to solve. Now we can start drawing our shear and moment diagrams. We're going to begin with the shear. Our shear will begin with the value of AY, which is 24 kilonewton. And then, then we're going to go 24 kilonewtons downwards over the course of 4 meters. That will bring us to 0. And this means our graph for A, B section is correct. Now we're going to draw our section BC. So for BC, we're going to begin with value of the Bx, which is 6 kilonewton. So we're going to go up 6 kilonewton. And then nothing's going to happen for the next 1.5 meters. And then we're going to go downwards 12 kilonewton, come down to negative 6 kilonewton. And then again, nothing's going to happen for 1.5 meters. And then we're going to go up 6 kilonewton. Then we're going to come down to 0. That means our curve for second portion is correct as well. Now that we have done that, we can draw our moment diagram. For moment diagram, our moment is going to begin at 0. Pardon me, not at 0, at negative 48. And from there we have this positive area, which is going to be 24 times half times 4, which gives us 48. So this means we're going to come up to 0 here, and our curve is going to be concaving downwards, second order. And then for BC section, our first area is positive, so it's going to be 6 times 1.5, which is 9. So we're going to go upwards to 9 kilonewton meter mark, and our curve is going to be first order. And then we have a negative order of the same magnitude, and we're going to come down to 0 again with the first order curve. And that means draw the shear and moment diagram for each of the member of the frame. Assume the frame is a roller supported at A and pin supported at C. To solve this problem, we'll have to solve each member individually. We're going to begin with member AB. Let's draw its free body diagram. So for member AB, we're going to have a roller at A, and then we have a point load from the distributed load, which is going to be 15K. And then B is a fixed connection, so we're going to have both horizontal and vertical plus a moment. So let's sum the forces in X direction. We're going to have Bx equals to 0. And then let's sum the forces in Y direction. We're going to have Ay plus By take by 15K equals to 0. This is going to be our equation 1. Then let's take moment about the point B. We're going to have moment B. Then we have counterclockwise 15K, 5 feet away. And then we have clockwise Ay, 10 feet away, all equals to 0. And nothing else can be done for this part. Now let's move to next part, our member, which is going to be member BC. So for member BC, we have pin support at C. We can have CX and CY. And then we have a point load of 2K halfway through. And then we have BX, which we already found to be 0. And then we have BY. And then we have a moment at B. Now let's sum the forces in Y direction. And we're going to have By negative and positive Cy equals to 0, which is simply Cy equals By. This is going to be our equation number 2. Now let's sum the forces in X direction to find our solution for Cx, which is simply going to be equals to 2K. And then we can take moment about the point B again, but this time for member BC. So we're going to have clockwise moment B, and then clockwise 2K, 6 feet away. And then we have Cx counterclockwise, and it's 12 feet away, all equals to 0. And solving for moment B, we're going to have our solution as 12K feet. Now we can plug the value of moment B into our equation. I'm going to name this equation 3. So we're going to have 12 plus 15 times 5 is 75. And then we have negative E times 10 feet, all equals to 0. Solving for AY, we're going to have our solution as 8.7K. And then we can plug the value of AY into equation 1, and we can have our solution for BY as 6.3K. Now we have all the required forces. We can go on to solve for our shear and moment diagram. So we're going to begin with shear. For shear, we begin with the value of AY, which is 8.7. We'll begin at 8.7K. And then over the course of 10 feet, we can go down by 15. So 15 take away 8.7 is 6.3. So we can go down to negative 6.3 with the first order curve. And here, BY is going to pump us up again to 0 because value of BY is 6.3. And now comes our second member, which is BC. So for BC, value of BX is 0, so we're going to remain at 0, and then nothing's going to happen for next 6 feet. At that point load of negative 2K is going to bring us down, and then again nothing's going to happen for 6 feet, and then CX is going to push us up to 0. And that's our solution for whole structure. Now we can proceed with the moment. So for our moment is going to begin at 0, and then we have this positive area, and there's this intersection. To find this intersection, we simply have to divide 8.7 with 1.5, and solving this we get our solution as 5.8. And now we simply have to multiply 5.8 with 8.7, and we have our n times by half because it's area of triangle. So our maximum is going to be 25.23, and it's going to be second order curve concaving downward. Similarly, we have this negative area, which is going to be 10 take away 5.8, which is 4.2 times negative 6.3 times half, and we get our solution as negative 13.23. Add 25.23 into this, and we have at the next 5 feet we come down to 12, and the curve is second order concaving downward. And here we have counterclockwise moment of 12, which is going to bring us down to 0. This means our first member's curve is correct. Now we're going to move over to next one. So for next one, we have clockwise moment of 12. So we're going to go down 12. And from there, nothing's going to happen. Nothing's going to happen for next 6 feet. And from there, then we have this area. Oh, one thing I did wrong is because a moment is clockwise, we're going to go upwards, not downwards. So we're going to be at positive 12. And then nothing's going to happen for next 6 feet. And then we have this negative area, which is going to be negative 2K times 6, which will give us negative 12. Negative 12 is going to bring us down to 0 over the course of next 6 feet. And our curve in this case is going to be first order